If you want to dive deeper and challenge yourself, these are not required, but for those of you who want to take a bend in the road or go deeper, I can suggest the following few exercises, which will take some of these lessons from this part of this lecture and take you a little bit further and try to see what happens in the case of amplitude errors and in the case of phase errors. We really only looked at here one or two particular types of coherent errors that you can see. This is by no means an extensive or comprehensive list, but I think is enough to give you the flavor of the core of the ideas of what happens with coherent errors in practice and how they build up and how they affect algorithmic performance. So feel free to challenge yourself if you'd like with these exercises, and feel free to post them on Twitter and reply back to me. I'll try to post the blog at some point with the answers to these. As we have seen, the quantum state or the wave function evolution is entirely deterministic. Schrodinger's equation is deterministic and gives rise to deterministic evolution. However, quantum mechanics departs from classical theory in exactly that it is not a deterministic theory. Rather, quantum prescribes a prescription for predicting the probabilities of observing a given result. And let's explain more about the consequences of this by using an example of the simplest system, the qubit, our favorite, continuing into the rest of the lecture to introduce quantum measurement theory and how it can explain a part of the effects we saw. Suppose you have the following idealized circuit where you have an initial state starting in the ground state, followed by Hadamard. As we saw, after a Hadamard, the state of the quantum system is going to be in the plus x eigenstate. We'll denote that by plus. And then we do a measurement. What comes out of the measurement? It helps to sometimes visualize the evolution. So this is the ground state, this is the plus excited state. So you notice that we're in a perfect superposition between 0 and 1 along the x-axis of the block vector. Now, to understand what happens here as a result of the measurement, what comes out as the answer of our measurement, we have to introduce the projective von Neumann measurement. Let's introduce quantum measurement theory 101 for the standard measurement that we do and think of. For the more advanced in the audience, I'll notice that there are more advanced types of measurements, and this particular measurement is going to be known as a von Neumann efficient, strong, and projective ideal measurement. This is how we typically think of the measurement as in a mathematic way. There's a little box with this meter symbol, and into this measurement comes in the state of the system. We'll denote that by psi, or later we'll talk about density matrices, so we can denote that as a rho. This measurement can ask different questions. So the measurement operator that corresponds to this, the observable, if you want, will denote by the letter M, capital M, or M hat. So this meter will measure in a particular basis, or it will measure a particular observable, M hat. And on the output of that meter comes out a classical variable or classical signal denoted by the double lines going to the right. So let's call that classical. And the classical outcome of the measurement I'll denote by the little letter m. Typically, the outcomes are either 0 or 1 for the observables that one looks at. So let's pick a specific example just to have something in mind. Suppose that our measurement observable corresponds to asking the question, is the qubit in the one state? The operator that corresponds to that is just equal to 1, 1. You notice that it takes the state 1 and returns the state 1 with an eigenvalue of 1. The way to actually understand what will come out of this is to really think of the eigenvalues and eigendecomposition of this operator. And the way we can write this is to say that this is 0 times the 0, 0 state, since our basis corresponds to having the 0 and 1 states, plus 1 times the 1, 1 operator. Again, as a matrix, in nice matrix notation, this will look like 0, 0, 0, 1. And the basis in which this is written is, of course, in the logical basis like this. So all of the 4 or 3 here different ways to write this represent the same actual object. You notice that what we've done here is kind of a nice, interesting decomposition known as a spectral decomposition. So we've written M as a sum on its eigenvalues. We'll call them M for lack of a better word, and their corresponding states or eigenstates M. For the particular operator we have here, the possible eigenvalues of the operator or the observable are 0 and 1. And the corresponding states M for this particular observable are also 0 and 1. And the way measurement theory works for these kinds of operators is to say that the possible outcomes that we could measure are given by the spectrum, the eigenvalues of the operator M. And so these are the possible outcomes. And each outcome, M, is associated with a corresponding state. And in this case, those states will be the respective 0 and 1 states. So what that means is that if we measure the outcome M equals to 0, then we can presume that we have found the state to be in the 0 state. We'll even see that the output of the state after this will be 0. This will be called the wave function collapse. Or equivalently, if we have a classical result that M equals 1, the outcome that we measure on our meter is 1, then the state that we've found is the 1 state. But what is the probability to measure 0 or 1? Because each time we do this measurement, we can only find one of the possible measurement outcomes, either 0 or 1, never anything else. We can denote that by saying 0, 1 here on the top. The way that this is formulated in the standard von Neumann measurement, and this is one of the postulates of quantum mechanics, if you want, is that the probability, I'll denote it here by a lowercase p, to have a measurement outcome M equal to 0 is equal to the expectation value of the state on the projector associated with that result. And I guess for our case, this is going to be the following: 0, 0. And then the probability to have M equal to 1, here, let's be more explicit. This is the probability of measuring the outcome, is the expectation value of 1, 1. If you want, sometimes these operators inside of here are also written in the following way as projectors, since they project the Hilbert space down onto this particular state. So this is the projector associated with M equal to 0. Maybe we should just denote that by capital pi sub 0 is just 0, 0. And the projector associated with the 1 state is equal to 1, 1. Where did we find or get these projectors from? Well, that's written from these are obtained from the spectrum of M. You notice that now we can write our measurement operator M, generally speaking, as a sum over all the possible outcomes, M, which are the eigenvalues of M times this projector on M, where in general the projector for the mth eigenvalue is just the mth state. So it's a slightly fancy way to rewrite what we've written above, but this generalizes to more complicated and interesting measurements. One of the key ideas here is also that the sum of these projectors, so we'll see that pi 0 hat plus pi 1 hat is equal to 0, 0 plus 1, 1. which of course in matrix notation looks like 1, 0, 0, 1. And you notice that that's nothing but the identity operator. And that's true in general, that the identity operator can be resolved in terms of the sum over all of these projectors. And that's because these observables are meant to be Hermitian operators. So here we have the following resolution of the identity. And the reason that that's needed is because you see that the probability of measuring 0 plus the probability of measuring 1 has to be unity, has to be 1. And that's because there's no other possible outcome. So if we do a measurement, we have to find a result. And so that will guarantee that P of 0 plus P of 1 is equal to exactly 1. And we can show that in a minute quite explicitly. Now, suppose that we take in the state psi. Let's write these out a little bit more explicitly, for example. So the probability here to measure the outcome m equal to 0 is equal to the expectation value. And let's do this, of the state psi projected on 0 in the following way, which you notice is nothing but the expectation value of psi 0 squared, like this. And again, the probability of m equals to 1 is equal to psi acted on 1, projected on 1 here. Psi is equal to, again, the magnitude squared of the 1 coefficient of psi. And so the probability of the two, so the probability of 0 plus the probability of 1, is equal to 0 psi squared plus 1 psi squared, which is nothing but the magnitude of the state psi squared. And we know that the state has to be normalized. And so this is always imposed and guaranteed to be 1. So we've simply shown that the probability of obtaining 0 must therefore be 1 minus the probability of obtaining 1. In other words, if we look at kind of a distribution of the probabilities to find a particular measurement result, of which there are only two, m equal to 0 and m equals to 1, then for a particular probability, let's say p, of finding 1, we must have 1 minus p of finding 0. And each instance gives us a different random bit. This particular distribution over what we can now think of as a random variable is called a Bernoulli distribution. And tells us that if we sample this random variable of the measurement outcome, let's here maybe just denote it by a capital M. Notice that there's no hat on this M, so this is a classical random variable. That corresponds to our measurement outcome. Then the probability of this random variable m is just given by this distribution. We'll call it here just Bernoulli of p, where p is this probability. This is maybe a little formal, but essentially all it's saying is that the graph on the left is mathematically written like this on the right. So we don't need to maybe bother more about that. What's a little bit more interesting now is to find out what's the expectation value of this random variable m. Suppose that you do this experiment an infinite number of times. Each time you obtain a 0 or a 1. What is the average expectation value of that particular variable that you're measuring? So we'll denote this, the random variable here as capital M. And lowercase m is a particular outcome of that random variable m. So let's do that. These are the statistics. Okay. The way we can denote this is to say that the expectation value, and this is now a classical expectation value over the random variable m, is equal to the definition of the expectation value. So the sum over every possible expectation value of m multiplied by the probability. And maybe it's confusing to use this p everywhere because I'm going to use the p up here as well as lowercase. Let's define the symbol for probability in the following to be a little double p like this, just so that we don't have a confusion in the notation. So I apologize that we have to use two different notations, but this capital P will denote probability. It's the function that will take the possible outcome and give us a number, and this P is actually the parameter of that distribution, but will be the probability finding the one outcome. And so this is the the expectation value of m is the sum over all possible m, which in our case go from 0 to 1, but let's maybe leave that as such, times or of m times the probability of finding m. And in our case, this is just equal to 0 times the probability to find m equals to 0 plus 1 times the probability to find m equals to 1. And we can denote this in the following way, that this is just equal to the probability of m equals to 1, which is what we'll define as lowercase p. Notice that by lowercase p here, maybe we should have written this up here, we're going to introduce that as our notation like this. Now, it's also instructive to note that the way to write this as well is to look up here and see what we mean by the probability of finding that particular value. And so using the expressions from above, we can write out this exact same expression as the sum on m times m. Now, the probability of m in terms of the state was the expectation value over that state of the projector on the nth state. You notice that that is the same thing as pulling out the projector, as, let's say, replacing the projector by its explicit construction, so m, n. And because the expectation value is a linear function, we can move the m inside, and the linear function, we can also move the sum inside. So this is the same as just writing that this is equal to the expectation, this is the quantum expectation value, over the sum of m times m acted on m, like this. Coming back up here, you notice that that's nothing but the actual definition of the operator m itself. Excuse me, right here. This is the spectral decomposition. And so the other way to write this is to just say that this is now equal to the quantum expectation value of the m hat operator. And so what we have now is a correspondence between the quantum expectation value, and in fact this is the reason it's defined in this way, and this is the expectation value of a classical variable. And this is also a, if you want, classical expectation value. But this is precisely why we define the quantum expectation value in this way, with this construction. This is all very nice. Essentially, we've sort of reproduced results we're already more familiar with. What's much more interesting now is what happens to the case of the variance or the standard deviation of this classical variable. Because this m is obtained as a sequence of random events, how much does the value fluctuate around that? It's not a deterministic number, but one that is a statistical random number. So to look at the variance, which I'll denote like this, of this classical variable m, we can write down the variance in the following way as the expectation value of m squared minus the expectation value of m squared, which we can write out explicitly, since we already know what the second case is. We know already that this here is just going to give us p squared, but we don't yet know the expectation value of m squared. So let's work that out explicitly. So here's the expectation value of m squared is equal to, just the definition of that is sum on m squared times the probability of having m over all possible m, which is going to give us, again, nothing but, if we work this out for the quantum case first, using the substitution of the substitution here of the probability to find m, and then using the linearity of the expectation value to move these in, we'll find that this is now equal to the expectation value of the sum on m squared, m, m, m. This is, again, nothing but the quantum expectation value of the operator m squared. And so notice that for the variance, we can now replace this here by saying that this is the quantum expectation value of m hat squared minus the expectation value of m hat then squared. Of course, the important factor here is to note that this square is outside the expectation value and this square is inside the expectation value. Working this out for our particular example, here I'll do it in gray. In our case, there are only two possible values. 0, so 0 squared is 0, and times the probability of that value, which is 1 minus p, but it doesn't really matter since this whole thing is 0, plus 1 squared times the probability of obtaining 1, which is p. So this is just going to equal, in our simple case here, and we might as well write it down at the very bottom, this is going to equal p squared. Putting this all together, perhaps it's confusing that we wrote that right below this line. Let's move that down. Let's move that down here to indicate that this is for our particular case. Putting this all together, then, the total variance of the classical measurement outcome in our case is equal to p squared minus or excuse me, not p squared. It's p minus p squared. There's no square here. Small mistake. Hope you caught that. Which is equal to probability p times 1 minus p. And notice that the variance is equal to 0 if p is equal to 0 and is equal to 1 if p equals 1, which makes sense because if the probability of obtaining the 1 state is exactly 0, that means we must be in the ground state necessarily, then the variance should be 0, meaning there's no fluctuations. So we have a deterministic answer. The variance is, of course, the standard deviation squared. I'll denote the standard deviation just by the letter sigma And we can put a subscript m if you want for the variable m, but it's not really necessary. So the standard deviation of the variable m is going to be the square root of p times 1 minus p. So here's a graph that shows us what this looks like as a function of the probability to measure the qubit in the excited state 1. You notice that we've plotted two things. We've plotted the standard deviation, and we've also plotted underneath that the variance as well. And so the blue curve here gives us the standard deviation of the measurement result. Call that sigma sub m. And the orange curve here gives us the variance, sigma sub squared. And you notice that the variance and the standard deviation are maximal at exactly 0.5 for the probability to find the one state. This is when we have a superposition, a maximum superposition between 0 and 1. And that's reflected in the variance of the measurements, in the indeterminism of measuring the one state, which is maximal here at exactly the value 0.5 and the value of a quarter down here as well. On the edges where we have a probability of exactly 0 or 1, we have a deterministic answer with no variance, 0 and 1. So we have this kind of random coin toss Bernoulli distribution whose parameters, the probability here at the bottom of being 1, is determined by the quantum algorithm, because this probability is essentially given by the overlap between the one state and the final state squared, which you notice is dependent on our algorithm. If we assume we start in the initial state and we have some unitary u, then the final state is just that unitary of the total circuit unitary u acted on the 0 state. This is the initial state. And this is the projection that's associated with the final state that we want to have an outcome for. So that expression is essentially rewriting the expression we have up here. Let's jump into a slightly more subtle but very key important point that will drive for us a large part of what we see in experiments, and will explain a large part of the curve that we're already so familiar with, that we've seen from the very beginning of this lecture, and that's projection noise and sampling noise. So let's turn to the example of a finite number of shots rather than the so-called infinite number of shots, or theoretical, ideally infinite number of shots we've looked at so far. Suppose we perform n shots of an experiment. That means that we repeat the experiment with the exact same unitary, assuming it's an ideal unitary, n times. Each time we obtain a single answer, either a 0 or a 1, and we'll denote that particular realization of the outcome as m sub 1, m sub 2, m sub 4, and so on. You notice that each of these is a random variable, if you want. We could call that random variable m sub 1, m sub 2, m sub 3, and so on. Doesn't really matter. This is just notation. And here I've depicted some sequence that I imagine. Suppose the first shot we got a 1, the second shot we got a 0, the third shot we got a 1, the fourth shot we got a 0, and so on. In fact, if we only drew 3 samples, there are a total of 2 to the third power possible number of outcomes, which are written here as 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. And each of these depict the number of depict the possible set of M1, M2, and M3. This is just to show you that these are all the possible outcomes. Now, if you do this experiment once, having 3 shots within that experiment, you'll get one of these sequences. And then you can ask, well, what is my expected value? And what is my variance on that expected value? Or how do I estimate it? The way that we can now, for a given sequence, estimate what happens is to look at the sample mean. And I'll write down the sample mean in the following way. By the way, suppose that we had this value. The sample mean will just be 0 plus 0 plus 1 divided by 3, since we have 3 3 results, and that will be a third. But let's define what we mean by the sample mean. Let's call it S, for lack of a better word or letter here, sample mean. This is itself a random variable because it will be given by 1 over the number of shots times the sum of over the, let's say, nth shot, the outcome of the nth shot, starting from n equals 1 to n. So for instance, for this particular realization, this is just 1/3 times 0 plus 0 plus 1, which is equal to a third. Okay. Mathematically, of course, we have it this way, and this is the definition of the sample mean here. But I will illustrate that this sample mean is a random variable. Because suppose that we didn't have the realization 0, 0, 1. Suppose we instead had a different realization. Maybe we had the realization 1, 1, 0. For that realization, the sample mean would instead be 1/3, 1 plus 0 plus 1, which is equal to 2/3. So we'll get a different sample mean, and in this case you see that there's quite a bit of a difference between the two sample means depending on what you have taken. So that's why we'll see that we need many, many shots, typically, many repetitions of the same experiment in order to have a faithful reconstruction of the mean expectation value. And let's look at just how many shots are going to be required to do this. So let's find the mean of the mean. So since the sample mean estimate here, this is the empirical sample mean, is a random variable, we can ask questions as usual, such as what is the expectation value of the sample mean itself? In other words, the standard deviation of our sample mean, or the error, the expected error on our sample mean, we'll write that like this, is equal to the square root of p times 1 minus p divided by n, where n is the number of shots. In other words, on the top here, we have the quantum projection noise. This is the fluctuation in our measurement that's purely due to the indeterminate nature of quantum mechanics when you have a superposition. That's the top of this expression. The bottom of this expression is just due to a very trivial classical effect, and that's because we've taken a finite number of shots. So we have two effects, the effect of quantum projection noise and the effect of finite sampling noise. But you notice that as the number of shots increases n, we begin to reduce and tighten the bound on the mean value. And this amounts to the error bar on the mean expectation value. So this is an important quantity to keep in mind, because for a given error, you can use this expression to find out how many shots you should take. Really see what this looks like on a curve represented here for the probability mass function of the sample mean as a function of, well, here rather for a probability of being in the excited state of p equals 0.5. So this is a maximal superposition, assuming that we took 101 shots. And the reason I've put this curly b here is because the sequences we're illustrating up here, such as these, follow from a very well-known distribution in classical probability theory known as the binomial distribution. We won't really need to get into that too much, but if you're interested in diving deeper, take a look at the binomial distribution. In any case, the probability, as you see, for having the value of the sample mean S is peaked exactly at the ideal value, which would be p equals 0.5. So this line represents the ideal expectation value, let's say E of S. But each time you run your experiment n times, one experiment here consists of n shots, 101 shots here. So you do 101 shots, you'll find a particular result, such as the sequence 0, 0, 1, 0, 1, 1, 1, 0, dot, dot, dot. One of those lands you somewhere here. Let's say maybe this particular one will land you over here at this particular blue dot. There's only a discrete number of possible outcomes you can find, just like as we saw up here with the case of the different results. And the most likely outcomes are those associated with the right expectation value. And the more shots you take, the closer you get. And you notice that the width of this distribution here is precisely given by sigma sub s, which is equal to p times 1 minus p divided by n with the square root. In fact, there is a nice movie we can take to watch with this. So here is an illustration of this exact same curve. This is an animation of the convergence of the number of shots for your expectation value. So if you have 0 shots, essentially you know nothing, which is why your probability is completely flat, the probability mass function, so it's nonsensical. If you only take 2 shots, they're essentially, well, let's put it this way. If you take 1 shot, there are only 2 possible values you can find, the value 0 and the value 1, each with a probability of 1/2. So that's why we have this here. As you now let yourself evolve, let's say maybe to 2 shots, there are now 3 possible values you can find. You can find with probability 1/4 the value 0 in the case that your sequence was 0, 0. You can find with the probability of 1/4 the value 1 corresponding to the sequence 1, 1. And there are 2 possible ways to obtain the expectation value of 1/2, which is that you found the sequence 0, 1 or 0 or 1, 0 of your measurement outcomes. You know, where the first here value corresponds to M1 and the second one here corresponds to M2. Now, if you keep doing this for more and more and more sequences, where we begin to increase the depth of the sequences and so on, you'll see that the distribution changes and becomes increasingly peaked. This is an animation as a function of n, the number of shots going linearly, and you notice that there are more and more possible values you could obtain, indicated here by the number of blue dots, but essentially they're just filling in the continuum, since each time we obtain a 0 or 1, up here, up until the total number of shots 101, and the distribution is getting narrower and narrower and narrower, proportional to 1 over the square root of n. So to have a 2 times smaller error, you need to take 4 times the number of shots, in other words. Let's illustrate what this looks like on our result from the previous section where we looked at the gate error. We saw that if we had a 3-degree gate error, we found the following sequence for the repeated X gate sequence. Now suppose that we take 800 shots. So at each depth, we have a different P. That P, the probability, is going to be equal to 1 minus the expectation value of Z divided by 2. That's going to be the probability to be in the 1 state, which will just be equal to 1 overlap with psi squared. So the probability P is going to be 1 minus the cosine here of d pi plus d epsilon divided by 2. that will give us the probability P. And for a particular realization of the measurements, we'll find out that now our curve looks like this, instead of it looking perfectly nice and smooth like this. For 800 shots, you notice that there are some fluctuations around the mean, and in fact those fluctuations depend precisely in the following way, as p times 1 minus p divided by n square root. That's the standard deviation of the fluctuations for a particular p. If you want to know what p is, we've calculated it down here. You notice that there are 0 fluctuations around the -1 and +1 values, since that's where we're pretty much in the ground state and in the one excited state. The maximum fluctuations really occur near z equal to 0, which is a perfect superposition of 0 and 1. And in fact, the precise error here that we expect to be bounded by is going to be 0.5 times 1 minus 0.5 divided by 800 with the square root. So this is exactly why we see that the curve looks pretty smooth at the top and roughly noisy on the edges. So with that, we've taken a really nice first deep dive into quantum measurement theory 101 and the limit of projective strong measurements, and we've seen how it can impact algorithmic performance and how you can estimate the number of shots that you would need for a given error here denoted by sigma. To dive deeper into this world of sampling and projection noise, and to understand the physics and computation of this a little bit better, I challenge you to try the following exercises yourself, starting with exercise 1 here, which is a set of calculations on the single qubit case, both on the sample mean, denoted by S. S here is a capital variable because it's capital because it represents the random variable of the sample mean, and capital V here to represent the sample variance, which is defined in the following way. You notice that the variance contains itself the random variable S. So this is a fun and a little bit tricky calculation, but you can do it. You find out whether or not this sample variance V is a biased estimate. You can find an expression maybe even for one that is unbiased. Do this also for 2 qubits to understand how this scales to larger number of qubits. And finally, this is a really fun and challenging, interesting question, which has to do with the Laplace rule of succession. And I challenge you to try that. And I'll probably post on this on Twitter or on my blog at some point what the solution of this is. Let's dive ahead right into state preparation and measurement errors. Since we've just talked about measurement theory, let's proceed by looking at measurements. And to do that, let's break out onto our favorite way to work, which is on the example of a single qubit. So here we have some general sequence which starts in the ground state, then proceeds to do a unitary, and then proceeds to do a measurement, symbolized by this meter. We'll assume for this exercise here that our measurement operator M corresponds again to asking, is the qubit in the excited state or is the qubit not in the excited state? So we'll denote that as M hat operator as the 1-1, which, as you can also check, is equal to the identity poly plus the Z poly, minus the Z poly. The plus would be the 0-0 operator. The classical variable that comes out on the output here is a binary variable. It's either 0 or 1, denoted by capital M. It has 2 possible outcomes. The probability of each of those possible outcomes for n being 0 or m being 1 is equal to 1 minus p, and p, where p is the overlap of the wave function onto the one state magnitude squared. Let's now look at what happens if our measurement apparatus is actually a little bit kaput, a little bit non-ideal, as is the case in real experiments. And in fact, our measurement apparatus has error that works like this. Suppose that the output of this measurement is m. which can either be 0, as we said, or 1. However, our measurement apparatus doesn't always give us on the output 0 when actually the state should have been 0. Instead, with some probability, let's denote it by epsilon, our error epsilon, we find that the bit we measure is 1. And likewise, with some error probability, and maybe we'll denote this as nu, we'll find that when the bit should have been 1, it actually ended up being 0. In order for the probabilities to all sum to 1, we have to have the probability of obtaining 0 when the result was 0 to be equal to 1 minus nu, 1 minus epsilon, excuse me, and the same for nu. We can denote the noisy outcome of our measurement as, let's say, a variable denoted by m tilde. It's supposed to be a little tilde here, so let's try to draw that again. This is the ideal classical outcome. And on the right-hand side here, we have the noisy classical outcome, which has some amount of confusion built into it. If we want to write this out slightly more mathematically and rigorously, let's now take into our view a way to write out the probabilities above in a simple way. That's just going to help us bookkeep. So let's say that the way we can organize the information here is to say that there's a probability vector. I'll call it P sub m, which looks like this. It stores the probability for the variable m to be equal to 0 in its first element, and in its second element, which is a column vector, is the probability for m to be in the excited state. So this is just equal to 1 minus p and p. On the right-hand side here, we're going to be interested to find out what the probability of our noisy measurement, m tilde, is equal to. So we can just write this as the probability to measure that, to obtain the outcome that m tilde is equal to 0, excuse me, and the probability to measure that the outcome m tilde is equal to 1. How are the two related? Well, following this graph here at the top, you can see that the way to obtain 0 on m tilde is by two different paths. One is that you did have 0 with probability 1 minus epsilon, and the other is that, the other case is that you actually had 1 and you had an error, a classical bit flip, with probability nu. So the way we can write this, if you'd like, is in the following way. So the probability to, let's just write out one element first. The probability to obtain that m tilde, the noisy version, is 0, is equal to the probability that we should have had as 0 in the first place times the probability of no error when we're in the 0. So I'll write this as the probability of no error in the 0 case. So 0 given 0. So we measure 0 given that we should have measured 0, plus the probability to measure 0 given that we had actually 1. This is the error probability times p of m tilde is equal to 1. And perhaps if it's not very clear here, let's rewrite these conditional probabilities in the following way. Let's write this as m tilde equals to 0, conditioned on the fact that m is equal to 0. And to be more explicit, let's do that here as well. This is the probability that m tilde is equal to 0, conditioned on the idea that m is equal to 1. Okay, we had a little typo there as well. This is essentially just representing the highlighted path above. Similarly, we can do this for the case of p of m tilde is equal to 1 by merely replacing in the conditional probability here the first element. This is m tilde is equal to 1 times the probability of m equals to 0 plus the probability of m tilde is equal to 1 times the probability of m having been 1 conditioned on an error. And you notice that the error terms here are the ones where we have a bit flip between the two. We'll highlight them like this. Excellent. Now, because of this matrix notation, we can introduce a really convenient way to represent this as a matrix equation. So we can write this in the following way. We can write out that the probability vector of the noisy M is equal to some matrix, we'll call it the A matrix, times the probability vector of the ideal case. So remember that this is the ideal measurement, this is the noisy measurement outcomes, and A is going to be our readout or measurement error matrix. And if we look at the two equations right here, we can extract out this expression more explicitly. You find out that this A matrix is just the four terms we see here. So let's write that out explicitly. Therefore, the A matrix, this is the measurement error, is going to equal, in this basis, is going to equal the probability, the conditional probability to have m tilde equal to 0, conditioned on m equal to 0. This is the no error case, so let's do both of those first. So here we can equally write the conditional probability to measure m tilde is equal to 1, condition on m being 1, and the error terms where we have a bit flip. So again, this is p of m tilde is equal to 0, condition on m equals to 1. That's the error term. And similarly here, p of m tilde is equal to 1, condition on m being 0. Okay, so if we're getting a little bit lost in the notation and the nomenclature here, what we can do, perhaps I'm mixing a lot of colors here, so hopefully I'm not getting over exposure of colors, but we'll try to reduce them in the following, is A is a map from the ideal to the noisy. So over here, if you want in our nice matrix notation to make this slightly easier, we can say that this is the case m equals 1, this is the case m equals 0, this is the case m tilde is equal to 0, and the case of m tilde is equal to 1. So think of it that way. Substituting in explicitly for the picture above here and epsilon and nu, we can write this out simply as the matrix of 1 minus epsilon, that's that error, epsilon, nu, and 1 minus nu. Notice that the sum on any the sum of any column of A is equal to 1, and this is to conserve the probability. So for any n, this is going to conserve probability. If there is no error, nu and epsilon are 0, and so this will equal just the identity matrix 1, 0, 0, 1 for an ideal measurement. You will notice that we can write the probability vector p of m tilde to also have a probability, which again we'll use a tilde on top to denote the noisy probability of the noisy output. And from this, we can find out what that noisy probability tilde is by multiplying through the X matrix here. So let's do that. So looking at the second column, or in fact, let's do that up here. For our case, we can see that this is going to equal, so P of m tilde equals 1 condition on m0, this term here, is equal to epsilon. Remember, that's saying that we have m equal to 1 when we should have had 0. So that's epsilon times the probability of m equals to 0. That's going to be this term. So that's epsilon times 1 minus p plus 1 minus nu, the no error case, when the qubits are down to 1, times p. And this whole thing is going to equal p tilde. So we can write out that p tilde, then, the noisy probability, and perhaps we're running out of space up there, so let's come down to the bottom here and express that. The noisy probability p tilde is equal to epsilon times 1 minus p plus 1 minus nu times p. Rewriting the terms and grouping together, we have epsilon minus p epsilon plus p minus nu p. It's going to then give us p, which is the no error case, plus epsilon, so there's a constant offset, minus nu plus epsilon times p. Let's see what this will then look like for us by looking at the difference between measuring the ideal case and measuring the noisy case. Let's look at what p tilde looks like as a function of p. So here we have on the y-axis the probability p tilde, essentially the probability to measure m tilde equals to 1, as a function of the probability p to measure m equals 1, the ideal case essentially versus, or the noisy case versus the ideal case. In the ideal case, we see that when the probability is 0 or 1, of course, we measure, in the case of no error, given here in gray, we measure exactly 0 and 1, respectively. And in the middle, we interpolate linearly. And so for every input value here, there's exactly one nice output value there, and it's quite easy to tell what it is. And they correspond one-to-one without any scaling or rotation. But in the case that we have an error, here an error of 8% to have a bit flip from 0 to 1, and a 20% error to have a bit flip from 1 to 0, we see that we have instead a very different curve that looks like a rotated and scaled down version of the gray curve shown in red, which doesn't span the same range. You notice that now you can never find a deterministic probability of measuring with certainty the value 1 as you could before, which would correspond to the 1 state here. We now, even when we are in the 1 state, in terms of the qubit block vector, we are going to, with 20% probability, still measure the 0 bit flip. And in fact, that's the best we can ever do. We're always going to have now randomness or uncertainty in our measurement that's not due to the indeterminism of quantum physics, but now due simply to classical readout error. And so we'll be limited in a narrower range here of probabilities for p, as opposed to what happens in the case of 0 and 0 here. And our ideal case then deviates from the noisy result by an error proportional to the difference between these two curves, which you notice is maximal sort of further away here on the edges for this particular combination. Let's return to the example of our repeated X gate, which is noisy, which we've seen now several times. Let's keep the same coherent error, but now let's add our readout error, assuming that we have an infinite number of shots. So that's why the curves look almost perfectly smooth. the sense that we have a nice, really well-reproduced sine curve here. But you notice that the span and also the start and end positions are very different. First of all, we don't have the same location for the maxima and minima in the y direction. So the measured maximum and minimum z values are really quite different. We'll see that this here is about the 5% error, and this here is about the 2% error. The 2% error, again, tells us the probability to measure 1 when we should have measured 0, and the 5% error tells the probability to measure 0 when we should have measured 1. So you notice how the span is squished, and also the center of this curve is slightly shifted. More generally, if we had a finite number of shots, we would also have a much larger error bar. We have finally made it to the last part of our road here on the journey ahead to the perhaps most interesting and fun part of our whole discussion, which is really going to launch us into a whole new field of quantum physics altogether, and especially quantum computation, and that is open quantum system dynamics. Open in the sense that we are no longer going to take the crude idealization that our quantum systems are perfect, ideal, and disconnected from the rest of the world. Rather, we will take into account that they're open, in the sense that, just like the story of the tree that falls in the forest and no one hears it, someone does hear it here. And there is always an environment, an observer, some sort of larger world in which the system lives, something to which it is coupled. And we'll see that while this story of open quantum systems, those that are influenced by noise in a way which we'll denote as incoherent, this has a very long history from the very start of quantum mechanics to today. There's some recent work from yours truly on the nature of actually what happens in one of the models that we'll look at. There's a very simple way to introduce the effect of any environment, to model its effect in a kind of probabilistic way, using the pure evolution that we're so familiar with already. And what incoherent here means is that each of those pure evolutions that occur for every time you run the circuit will now be combined in a way where they can no longer interfere among each other. There's no longer entanglement between the different instances of the circuit, since they're different instances of the circuit. But at each instant, we can think of a pure state, a wave function, and we can combine all of them together into one large ensemble, an ensemble of quantum trajectories. Maybe that's a bit too much introduction, so let's just dive in and show by example how this works and what this can describe. But this will describe one of the key parts in understanding noisy gates, noisy circuits. And here you see my depiction of a very simple circuit, which starts in the ideal ground state, followed by one noisy gate, and then measured. Now, for this section, we'll take a different model from that which we took in the section for coherent noise, where we took a unitary for the noisy gate, noisy again denoted by the little tilde here on the top. In this section instead, we're going to think of this noisy gate as two pieces. One, which is going to represent the noise, denoted here by this curly n. Sometimes you'll see in this notation there's a curly epsilon, followed by the ideal gate, G, and then measured. Now, this noisy box here, representing the noise, denoted in red here, doesn't necessarily have to be a unitary gate anymore, as we'll get to in a minute, but can, when we wrap these trajectories together, represent something we'll call an incoherent noise. And it has the following model. You can think of it this way. Here's a very simple example where you can say that what this noisy box means is that each time you run the circuit, you will either apply the identity gate when you go through your circuit in steps with some probability denoted by 1 minus p, or alternatively, you'll apply the bit flip X gate. This is one particular model of our noise here. But let's see what the following construction gives rise to. Because you see now, each time you apply your gate in each realization, it's going to be preceded by a random action on the state, a known deterministic action in of itself, but a different one at each realization. And you as the observer and the final recipient of the classical bits here don't know whether your measurement outcome M came from this circuit or this circuit. We're going to be ignorant to this information. And so we have to lump in all that information together so that the probability of this outcome M will actually depend not on one state, but on two states. Suppose that this is something we denote by case A, and this is something we denote by case B, then the probability of the meter here depends on the state, let's call it the final state psi sub A. The probability of the meter down here depends on a different state psi sub B. And then both of those will somehow play a role and combine into telling us what the probability of the final measurement observable we will find out is. Of course, in each case, you can think of there's a measurement observable. There's a measurement outcome A, there's a measurement outcome B, and we get one of the two. In this case, we get MA with probability 1 minus P. In this case, we'll get the measurement observable MB with probability 1 minus B, but we don't know which of these two states we're going to be in. The density wave function, the density matrix rather, is one powerful way to combine all of these results together, as we'll see in a second. But first, let's work out a very simple example of how this looks. Keeping in mind that here we're going to look at some gate G. We'll take two very, very difficult examples in mind, either the identity or the X gate. Now, for our model of how the noise here will act, and I'm going to change notation here and denote this by epsilon moving forward. So excuse my notation here. Let's denote this by a calligraphic curly epsilon. Moving forward, we can think of two different ways that the circuit can occur, having, let's say, case A and case B, with these two realizations. And then we'll come back to the example of repeating the gate G over and over and over again. Now, let's do it first by the pure state. Suppose that the gate G, for our example, is going to, in the ideal case, equal just the X gate, the bit flip gate. Well, then you can see that our effective gate in the first case is going to just be the following. So our total unitary that corresponds to the circuit is the identity followed by G, which is of course just G, which in this case is just equal to X. Notice, as usual, you read circuit diagrams left to right, but you read algebraic multiplication right to left, since the state vector is going to be on the right-hand side when you apply it. The unitary on the bottom is going to, in this case, be G times X, which is going to be, in our case, X times X, which is the identity gate. So there's a funny flip. So in one case, with probability 1 minus P, you apply the ideal gate. And here with probability P, it just so happens that your error makes it so that you don't do anything. Well, that's bad if you wanted to do something and then suddenly you're not doing anything. These are your two possible unitaries for your initial state 0. So clearly, if you start in 0, and in this case, you'll end up in the 1 state, and in the other case here, you will end up in the 0 state. And your measurement outcome will, in the first case, be, oh, in this case, it happens to be a deterministic outcome. It doesn't have to be that way, but in this case, your deterministic outcome will with certainty be 1, and in this case, the outcome will be 0. So you see that the error in this case has rendered us totally bonkers. It's pretty quick to note right away what happens to our kind of measurement observable in final case. Since we can't tell the difference between the two, if we run this 1,000 times, we'll get a sequence of 0, 0, 0, 1, 1, 0, 0, 1, etc. Some kind of distribution. And if we look at the average value of our measurement observable here, which is just
as the usual 1, 1. Then we'll find out that this is equal to 1 minus p times 1 plus p times 0, which is equal to 1 minus p. Is the probability of the error. In the ideal case, and maybe to denote that as the noisy case, we'll put a little hat on it. Of course, in the ideal case, what we should have had is the first case. So let's do m hat with no tilde. So this is the ideal. And this is going to give us then just 1. So you notice that the probability, the difference in the two is p, it's the amount of error you have. Maybe to also make it a little bit more clear, let's just imply here that 0, 0, 0, 1, 1, 0, etc. This sequence gives us one result or one circuit instance. The circuit instances in this case are quite easy to label since the answers happen to be deterministic and it's easier to illustrate. But clearly here we have B, 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 case A, B, B, A, and so on. This was the realization of the actual circuit we applied. Remember that we have no control over this. Our intended circuit is just to apply G. Now, you notice that the way the two cases combined was to say that, well, I could have the outcome 1 with this probability of no error, and I could have the outcome 0 with this probability P of having an error. And so this here is the no error case, and this here is the error case. That's at the level of the classical outputs. Wouldn't it be nice if you could also similarly combine your states? And that's where the density matrix comes in and allows us to combine the statistics of having different pure states into an object that can keep track of what's happening in each trajectory, in each instance of each pure state, while also keeping track of the probability of having that state. And let's define that this way. Across all the ensembles, which are either type A or type B, the initial input state, so let's call it rho sub 0. This is going to be our input state. Oops, let's actually draw that. Let's draw that over here. Our input state is always the same. It's just the state 0, which I could write in the following way. It's 1 minus p, since that's the probability of having case A, times 0, 0. 0, 0 is just the density matrix version of the pure state 0. Remember that for pure state, the density matrix of a pure state psi is written like this and is equal to, in matrix notation, if you have a vector, let's call it the vector psi, which looks like this. You can write this as psi dot psi conjugate transpose. And so this will become a 2x2 matrix, which we saw slightly earlier, which will look like this. Let's write it in the following way. Cosine of, well, let's actually write that out. Suppose that we have the state psi is equal, just to be explicit, suppose the state psi is equal to the following parametrization. Cosine of theta over 2, sine of theta over 2. And then we can add a phase for the block vector. Of the block vector, we typically write as e to the I phi. Notice that the input of psi acted on psi is equal to cosine of theta over 2, sine of theta over 2 e to the I phi. dotted into the column vector version of this, which is equal to cosine of theta over 2 squared. There's a minus here because we've complex conjugated the left side. The right side here is the same, plus sine of theta over 2 squared times e to the minus I phi times e to the plus I phi. So those terms cancel out. So this is just equal to cosine squared plus sine squared of some argument. We don't care what that is. And that's, of course, equal to 1. So this is unit normalized. Great. If you're wondering what the angles are, and we've gone on a slight digression here to show, again, more explicitly what the Bloch vector is, but this will be a useful parameterization and representation for the following. It's maybe important to keep in mind that these angles for theta and phi are constrained so that you have a unique covering. There's only one point on the sphere that corresponds to one pair of angles. The angles of theta go between 0 and pi, and the angle phi goes between 0 and 2 pi. So there's a little bit of a difference between the two. And the way you can also visualize this in terms of the Bloch sphere, where the state psi, or as we'll see in a minute, only the state rho, has the following form. The angle between the z-axis and this Bloch vector here is equal to theta. And then the projection of this vector in the xy plane, like this, is going to give us the definition of the angle phi. So you can see why phi goes between 0 and 2 pi, since you can go from plus x to plus y to minus y to minus x to minus y, and then back to plus x, whereas theta goes from plus z to y to minus z. Z being, of course, this direction as well. Great. So finishing this, if we multiply out now what the following looks like for the density matrix, let's say rho, we can write it as psi acted on psi, tensor product, if you want, with the complex conjugate. This looks as such. We'll take on the left-hand side the cosine of theta over 2, sine of theta over 2, e to the minus I phi, and we'll multiply it by cosine of theta over 2, running out of space, sine of theta over 2 e to the minus I phi. Excuse me, this one should have been a plus, the complex conjugates, plus I phi. Now, multiplying these together, we'll find that row times column will give us the first element. So row in 1 times column in 2 will give us cosine of theta over 2 squared. Then row in 1 times column in 2 will give us cosine of theta over 2 sine of theta over 2 e to the minus I phi. Continuing this, on the bottom left, we'll have the same thing except with a complex conjugate. So we'll have a cosine of theta over 2 sine of theta over 2 e to the plus I phi. And then on the very bottom right, we'll have a sine of theta over 2 squared. We can simplify this. Cosine of theta over 2 times sine of theta over 2 is equal to 1/2 sine of theta. Then we can find out that the density matrix of this pure state is going to look like cosine of theta over 2 squared, sine squared of theta over 2. And here we'll have 1/2 sine of theta times, sine of theta times the cosine of phi minus I sine phi. And here we have the Hermitian conjugate of that expression. Now, I challenge you to yourself try to show that this is going to equal the following. This is 1/2 times the identity poly, or the identity matrix, plus, let's call it x, a lowercase x, which I'll define in a second, times the poly x operator plus y times the poly y operator plus z times the poly z operator. You notice that the polys are actually going to form a complete basis of all the functions, of the function space that can act on the Hilbert space. And the following x, y, and z coefficients are going to be the following. X, y, and z, lowercase x, y, and z, will equal cosine of, sine of theta, cosine of theta, times sine of, times cosine of phi, times sine of phi. Okay, you can pretty much read off the x and y terms from the diagonal here. You notice that if you remember x, the x poly has the form of 0, 1, 0, 0, 1, 1, 0, and that's going to be the following. That's going to essentially be this times this. The 1/2 we'll get rid of because of the overlap between the two states, since the trace of the identity in this qubit case is equal to 2, and the trace of x squared, which is equal to the trace of the identity, is going to equal to 2. This is a normalization, if you want. Using the properties of the polys, you can also show that the x is just equal to the trace between the x poly and rho. The y is equal to the trace of the y poly times rho, and the z coefficient is just equal to the trace of the z poly times rho. So these form a nice basis for us. And this is a very nice general construction to write the block vector in the xyz coordinates. So we have yet another way to write this point here, not just in terms of angles theta and phi, but also in terms of the points x, y, and z, which are given by the expectation value of the x, y, and z polys. The expectation value in the case of the density matrix is given by these trace constructions. With this nice little digression on the block vector, let's come back to the initial state and then look at how the later state of the circuit looks like. Initially, we have that rho 0 is equal to 1 minus p 0, 0. One way to think of this state 0, 0, if you look at the construction below, is to say that the angle theta is equal to 0 and the angle phi is equal to 0, or we have the point of 0, 0, 1 in the xyz space. The key element here is that with the density matrix, we can simply combine the pure states. This is psi a0, the initial state in the A case, plus the state at a later, at the alternative configuration, the B1, which is in this case identical. It's just 0, 0. So we just have, again, the pure state of the B circuit at circuit depth 0, weighted by the probabilities. In this case, since we have the same state across all the different parts of the ensemble, the initial state, of course, is just 0, 0. What's more interesting, of course, is to now look at what happens to the state after the application of each of the gates. We saw what each of the gates should give us. In one case, we had the application of the total unitary U, which in case A that's denoted by U sub A and U sub B, was X, and in the second case was the identity. Let's combine those as well. So looking at each of the cases and resolving that here on a case-by-case basis, in case A, the final state, which we'll denote by just psi sub A, is equal to the unitary of the A instance acted on 0, which we said resulted in 1. And we can write this as rho sub A is just equal to psi sub A, which is equal to the matrix 0, 0, 0, 1. And in case B, we can write it as psi sub B is equal to the unitary in the B case acted on 0. It's equal to the 0 state, which is going to give us the density matrix of the Bth configuration, which is psi B, which is equal to 1, 0, 0, 0, 1. We now get to simply combine the two cases weighted by their probabilities for the ensemble. So the final state, which we can no longer write as a pure state psi because we have mixtures of states, but we can write as just a mixture of the two, denoted by this density matrix rho, is going to be the probability of the A case times the density matrix of the A case plus the probability of the B case times the density matrix of the B case, which in this case is just equal to 1 minus P times psi A, pure states, plus the P, the probability of an error, times psi B, which is, for our purposes, equal to 1 minus P 0, 0, plus, 1, 1, plus P times 1, 1. And that's the final state. We could also write this in our matrix notation as 1 minus P 0, 0, 0, 0, 1 plus P times 1, 0, 0, 0, which is then going to equal P 1 minus P 0, 0, written in the logical basis, which I like to write in nice matrix notation in the following way. If you'd like to be more explicit, what this notation means is that the density matrix is then equal to this line here, where the term P, and we have this is good little catch, excuse me. We should have quite the opposite here. I see we've made a little mistake. So yes, in the case of an error, we are actually in the ground state. So this should be 0, 0. And I think we've caught the error right after that. So let's instead fix it in the following way. This is going to be reversed. So this is P, the probability of an error, and this is 1 minus P. This is where we should have ended up. Tracing that P across all the steps, we find ourselves like this. In terms of what this state looks like on the Bloch sphere, we can again look at the Bloch components. Of the x, y, and z Bloch components, which is going to just equal the trace of x hat on rho, the trace of y hat on rho, and the trace of z hat on rho. you notice that the first two terms must be 0. Because those matrices are orthogonal, we can try it as an exercise, or keep in mind always that the trace between any two poly operators, we'll call them P alpha and P beta, is equal to delta alpha beta times 2 in the limit that, or in the case that alpha beta are in the indices x, y, and z, and P alpha and P beta are just those subscripts. Let's write out more explicitly what the trace here looks like. So this is going to equal the trace of z times rho. Remember that that's 1, 0, 0, minus 1 times p 0, 0, 1 minus p. That's going to equal the trace of p minus 1, 0, 0. The trace is just the sum of the two terms on the diagonal. And so this will be 2p minus 1, which you'll notice is equal to minus 1 if the error is 0p. There's a very nice visual way to interpret this and to see this, and that's to recall that in the first case, in case A, we have following block vector. This is depicting the wave function of case A, or the density state of case A, which is just equal to 1, and points to the North Pole. This occurs with probability 1 minus p. Now with probability p, instead we find the case B block vector, in which case we have the zero state. This is depicting psi sub A or rho sub A. This is the probability. That's my little times multiplication symbol. It's not an X. If we just sum these two vectors together, weighted by their respective probabilities, then we'll find out that we find an average vector that looks like this and has length of 2p. Excuse me, that is not the right vector here. That is a different vector. The one that we will find for our example is going to point down from the center of the block sphere and will have length minus 1 plus 2p. And so the error is going to be 2p. Notice that the block vector length now is no longer 1. For all the pure states that we saw so far, if you computed the expectation value of x squared plus y squared plus z squared on all the pure states, that was 1 for pure. Now the purity is lower, and you notice that if we compute the expectation value of x squared plus y squared plus z squared, which is just the length of the block vector squared, for our case, the first two terms are 0, so we get only the expectation value of the z squared, which is 2p minus 1 squared, and this is equal for our impure state. And so the purity will go down to exactly 0 if the probability of the bit flip is equal to 0.5. The block vector length will be 0. If the probability of a bit flip is 1, it's a deterministic thing. So even though we'll get the wrong answer, since it won't be the gate we want to implement, we won't lose coherence. Which is represented here as a block vector that isn't on the unit sphere, but is going to be shorter. It will live inside the sphere. The other thing that's maybe quite nice and important to notice is if we come back here and we try to think about how does the unitary act on the state, you notice that in both cases we could have written the final state here. I'm going to extend ourselves here to the right in the following way, as 1 minus p, and substituting in, we have u acted on the initial state 0, u in the case A, plus p times u in the case B acted on the initial state 0, 0 times ub keeping in mind that psi sub A is equal to the unitary of the A circuit times the initial state, and similarly psi sub B is equal to the unitary of the B case times the initial state 0. More generally, of course, we could write this in the following way, that the probability of case A times the unitary of A times the initial state, whatever that is, 0, 0, times UA, excuse me, we're missing daggers here. We need to have those since they're acting on the bra part as opposed to the ket part of the state, acting on the right. Of course, you can see that directly by writing that psi A dagger is equal to psi A. And on the left-hand side, if we substitute in U0 daggered, then this will equal now the following: 0 daggered U daggered, which is just equal to 0 U dagger. Just like the matrix transpose, when you have A, B, dagger, you have to flip the order of the terms to propagate the dagger through each of the elements. Excellent. So keeping this in mind and seeing how the unitary just acts from the left and from the right, we can think of a general way to represent this. Since you see that the input state is always 0, 0 in both cases, but the way that the evolution happens now is not by sequence of unitaries, but by unitaries happening in parallel that cannot mix. So there's a way to write this channel, as I'll show us in just a second here, as soon as we complete writing the final part of this expression. One way to then write the action of the channel on the input state from these expressions up here is to write it as an operator that acts on an input state, a density matrix. So we call that a super operator if you'd like, because it's super in acting on density matrices as opposed to states. And we'll call that the error channel. And we'll see that in our case, epsilon on rho in is equal to this 1 minus p, or let's write it a bit more generally, as a sum over all the cases, which here we can denote by the letter k, of the probability of having that kth circuit occur. The unitary associated with that kth circuit acted on rho in times UK dagger. And this is the more general construction of what we had just seen up above here for the case of two different cases. For us, K was simply in the set A, B. And notice that now rho takes a density matrix to a density matrix, or a block vector to another block vector, which can be shortened. We can apply this several times. We can apply the gates several times in order to reconstruct what happens in the case of our repeated sequence, where we now want to apply the noisy gate G D times, and then measure. One way we can do this easily and quickly and think of this is to say that we can try to understand the action of our noise channel, epsilon. So we can write our noisy gate G in the following way, that G is equal to this noisy channel, epsilon, acted, or rather followed by our ideal X gate. For some input state rho in. So let's take a general density matrix input state, rho in, which, as we saw up above here, can be written in the following way, where X, Y, and Z don't have to be states that live purely on the surface of the block sphere, but can live within, as illustrated by the example here. So let's say that our input state is just 1/2 the identity plus some x in x hat plus y in y hat plus z in z hat. And we can drop the in subscripts in just a minute so we don't get too complicated. And let's find out under the action of the output, under the action of epsilon, what the output state is. For our case of the two unitaries that look like this. And we can write this out in the following way. So this is going to be 1 minus p times the action of the channel in the case that we have no error, which is just the identity operator acted on row in times the identity operator. Well, that's trivial, that doesn't do anything. Plus p times the bit flip x acted on row in. And remember that the way you should think of these here is, in this case, we're just applying the unitary gate x on that circuit, on that density matrix input. It's easier maybe to write this in the notation of the block vector. In the first case, we have 1 minus p times x, y, z. If you want to be more explicit, we can denote these by in. X, y, and z contain all the information there is about the input block vector. And one way to write our density matrix, if you'd like, coming back up to the picture above, is to say that rho is equal to 1/2 I plus x times x hat plus y times y hat plus z times z hat, which is then equal to 1/2 1001 plus x 00 plus minus iy 00 and plus z minus z 00, and this is then equal to 1/2 1 plus z, 1 minus z, and x minus iy, and x plus iy. So we've just written the general sort of form of construction here of the density matrix for an arbitrary qubit state. It could be a pure state or an impure state, with the parametrization that x, y, and z are numbers between -1 and 1, and x squared plus y squared plus z squared has to be less than or equal to unity. Then that will contain us to be a pure state or a mixture of pure states. So then we have the action of the x gate, which is going to act on this input state x, on this input state rho. On the side here, we can compute that. So if you take x acted on rho, you notice that we have 1/2, we have x acted on 1/2 identity plus x times x hat plus ... acted on x. So we can write this out more explicitly as moving the x inside. We have 1/2 xix plus x conjugated by x plus ... We'll see that the identity and the x gate commute, and they don't do anything to each other here. So this is just the identity, since x squared is the identity also. So that's easy. X and x also commutes, and x squared is the identity. So similarly, this is just, again, x times x hat. So those two components do not get affected. And we'll see that the other two components, if you work it out, and I challenge you to pause the video and explicitly write out the multiplication of the matrices here, will give us the following flip. And so in the case of our input density matrix will have P times X in, which remains unaffected. We'll have minus Y in and minus Z in. So you notice how the bit flip here will flip both of those components of Y and Z and leave invariant the one around which we're doing a rotation, which is the X component. Combining these three components together, we can then find the following. We'll have 1 minus 2p times X in. We'll have we're making too many little mistakes today. This has a plus sign and will cancel with the p here. So we'll just have X in, Y in, Z in, multiplied by, in the first case, nothing, just the identity. In the second case, we'll have 1 minus 2p. And in the third case, we'll also have 1 minus 2p. In fact, these are our error terms. This is how the error will propagate. This is the action of the noise channel epsilon here, acted on the block state. So this is what epsilon does. We saw exactly the same case up above here. We had the Z state shrink by essentially 1 minus 2p. Now we see the generalization of that to any input. So the effect of this noise channel epsilon is to shrink the block vector in the Y and Z directions by 1 minus 2p, or whatever input state we have. We can visualize the action of this noise channel then on the block sphere in exactly this way, where any pure state that starts at the unit on the surface of the unit sphere will then get shrunk like this in the Y and Z directions by 1 minus 2p and 1 minus 2p, p being the probability of the error. Anything in the X direction, however, is unaffected because the X gate can't flip the block vector in the X direction. And so this is the way you can think of now this noise, and this is kind of a generally extensible notion that incoherent noise will tend to shrink your block vector, or will tend to shrink your density matrix in some direction that dictates the force in which the noise acts. And this is what happens in the case of bit flip noise generated by X. So let's return now to using this in the case of our ideal circuit, repeated circuit D times. Intuitively pause and think about what might happen. Well, you see that each time we apply the noise, the block vector shrinks. So if we apply the gate n times, or D times, we'll have the shrinkage applied D times. So we'll increasingly shrink, 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 shrink. Let's apply now also the evolution of the X gate into this picture. So let's look at what the X gate applied to the density matrix will do. And we'll see that for an input state rho in, it will just take, it will do the following, which we calculated up here to the right, by the way. It will take your X in and leave it as X in. It will take your Y in and flip it to minus yn, and it will take your zn and flip it to minus zn. This is a very useful representation when you work with qubits, to just look at the action on the block vector itself. Now, if we combine these two together and apply them n times, you could almost, if you want to think of this as two matrices applying to the state. Let's look at now what our noisy gate G, I'll write it like this. Our noisy gate G acted on rho as a function here, which is equal to our first noise epsilon of rho, then acted on by the X gate, applied D times well, let's write it in the following way, g to the power of d. Then we'll have this construction here applied d times. So then we'll have epsilon of this, x of this, dot, 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 sort of done d times. We're running out of notational space here. This is going to give us, for the input state that we have in mind, or actually let's do it for a general input state. It should be sufficiently easy enough. We'll have the following. X in, y in. X in doesn't get changed by either the first case or the second case, by either this or this. It's only the y and z components that are going to be affected. So then we have yn will be negative 1 minus 2p to the power of d, and negative 1 minus 2p to the power of d times z in. And that's going to give us what our final state will be, rho final, at d iterations of the noisy gate. If we take in, to simplify, that the input state is just 0, 0, the ground state, or in Bloch vector notation is 0, 0, 1, then the final state, after having applied the gate and the noisy channel d times, will then be the following. Will be 0, 0, since we see that there's no mixture of the different components, and 2p minus 1 to the power of d times 1. And so the measurement of the average expectation value of z, the expectation value of z, is equal to the trace of z rho in, is then equal to just the z component, which is 2p minus 1 to the power of d. Notice that if p is equal to 0, then we recover the earlier result that z ideal is equal to minus 1 to the power of d, the depth of the circuit. But what's going to happen now is that we have a decreasing curve, because p is a number that's going to be probability between 0 and 1. We'll assume that p is small, and so the expectation value will shrink proportional to the rate p. Since we have now an exponential function in the error, the final expectation value as tilde z hat in the case of the noisy state. This is for the noisy output. We'll note that 2p minus 1 to the power of d for the case of small error is approximately equal to 1 minus 2d times p. P is the probability of an error. And this has a very different functional form from coherent error. Notice that this is now linear in the error, linear in p, as opposed to coherent error, in which the noise was quadratic to lowest, in the worst case, with p. So this is a general statement about the way incoherent error builds up in your circuit. It has a linear impact on your algorithmic performance as opposed to quadratic impact, as in the case of coherent error. So let's return to our original example where we looked at coherent error of 3%, the repeated gate d times, and we looked at also now to add incoherent error at a rate of 0.012 per gate g. So we see that because of the coherent error, again, we have this oscillation. But unlike the example that we saw earlier, this oscillation is now damped by an exponentially decaying envelope, shown here like this, that goes at a rate of 2p minus 1 to the power of d. Or, if you want, just the magnitude of that. So the effect of incoherent noise is to shrink your Bloch vector, and here, in this case, shrink your expectation observable to do this. Now, incoherent noise doesn't always have to shrink your block vector. Actually, it can sometimes take you into a particular state, such as the ground state. It can deterministically drive you towards that. To give you a sense of different noise that you can encounter and experience, what we covered so far was bit flip noise when you have the probability P of having a random X gate applied to your circuit. But imagine that instead of an X gate, you applied a Z gate. Z gate will do almost exactly the same things we saw, except that the labels of X and Z will be flipped. And I challenge you as an exercise to work out the action on the block vector under the following model. If you do that, you notice that instead of the lobe of the shrunken pure states under the action of the noise being in the Z and X planes as before, they'll now be, in the Y and Z planes as before, they'll now be in the Y and X planes for phase noise. So phase noise has a different structure. Another very important and interesting amount of noise is, well, what if you don't have just two possibilities, but you have four, essentially every possible gate in the poly group that you could apply, with the probabilities P quartered to have the X gate applied, the Y gate, the Z gate, and also the leftover probability is that there's no error. This is the model. I challenge you for your exercise to try to work this channel out and its action on the Bloch sphere. And you notice that it's symmetric. It symmetrically will push your pure states towards the origin of the Bloch sphere, shrinking you at this rate. And more generally, another very useful model is that of stochastic polynoise, where you relax the symmetry assumption and say that, well, I could have an error in the X, Y, or Z directions that occurs with different probabilities, P sub X, P sub Y, and P sub Z, respectively, occurring with these circuits. And that will give you, again, the same qualitative structure that instead of pure states on the unit sphere, you're going to, after the application of the channel, end up with states that live within the Bloch sphere that are deterministically shrunken, here depicted for these values of the noise. But now you've reduced the amount of symmetry in the. With this, we've come to the end of our journey today, to the end of our lecture, but the beginning of your own journey. We've covered a lot in one short series of lectures. Hopefully you now see all the elements that went into this real experiment, from state preparation and measurement noise, which gives us these fluctuations, as well as some of the offsets of the range here and the z-axis. Then we also covered coherent noise, which gives us this quadratic buildup. In the error, we have this incoherent noise that we just covered, which can be understood in terms of quantum trajectories and will deterministically shrink your vector to the middle. The application of those gates is called a quantum jump, when you have a jump from the 0 to the 1 state stochastically. You notice that if you look at a Nature paper from a few years ago titled To Catch and Reverse a Quantum Jump, in fact, those quantum jumps are not as random and unpredictable as once thought, but there is some coherence and predictability to those quantum jumps. So I encourage you to take a look at that if you'd like. Then we have projection noise, which gives us some of the variance for a finite number of shots. And finally, when we have all of these put together, we have to carefully think about the difference between our ideal expectation value, which might be, say, unity or -1, and what happens as a function of the complexity, depth, and width of the circuit, which will be reduced. As we understand that noise in the case of the A matrix, we saw that if you invert the A matrix and apply it to the result, you can undo or mitigate the noise in the average sense. And that led us into the understanding that if you can also understand and master these, you can perhaps move towards the road of no noise. And finally, in the most general sense, there are quantum error correction algorithms which can altogether protect you fully against noise, given that you have enough resources to implement the algorithms above their threshold. With this, we come to your next steps. There's some lab work with Qiskit, run real experiments on devices, stay in touch with us, check out the references and problems given in the lecture, and take some of the dangerous bends that I've suggested to explore deeper if you're interested. Stay in touch. Thank you very much. And don't stop questioning. I'll leave you with this quote.
on the nature and importance of curiosity. And keep in mind that here we've shown you one path into this world. And I hope that you will explore more, enjoy it, have fun, and comprehend a little bit more of the mystery of quantum each day. Let's now look at an example of a 2-qubit gate error, one that can cause a new type of feature, an entanglement type of error. This is the example circuit will take in place, and this is actually one that's quite practically relevant. The H gate here denotes the Hadamard gate. In the nice matrix and in the logical basis, the Hadamard gate looks like this. And if you look at what it does to the zero ket, essentially you're going to ask yourself, what is this? Oops, that is not the pen we wanted. We wanted the highlighter. So this operation here, acting the Hadamard on 0, will give you the plus x state, sometimes just denoted by plus. That's going to be the first column of this matrix. And if we want to know what the Hadamard looks like when acted on the 1 state, that's going to give us the second column of this matrix. And that's going to be the minus x state. In any case, let's follow through the example here and see what this looks like. And to do that, let's break out for more detail and depth to the note. Let's follow through step by step what this quantum algorithm looks like. At the very initial time, at time essentially 0 here, we're going to start off by being in the state 0, 0. I've implied a tensor product between these two. After the application of the Hadamard gate, essentially both of these unitaries will act independently on each of the qubits. So the first Hadamard will act on the first ket. The second Hadamard here will act on the second ket here. We use our rule on the right-hand side here. So after this first step of the circuit, we'll be in the plus x state. Sometimes this is just denoted as plus plus to indicate the plus x state. And I say it's the plus x state because I encourage you to check for yourself that the x Pauli acted on the plus x state will give you plus 1 times the plus x state. In other words, it's an eigenstate of x with an eigenvalue of 1, and the x Pauli acted on the minus x state will give you minus 1 times the minus x state. And again, maybe just for completeness, let's also note that the plus x state is sometimes denoted as just plus, and the minus x state is sometimes just denoted as minus. These are equivalent. This is not an official symbol, but I'll temporarily use this kludge here to denote that. Now, after that, suppose we have just some idle time on the quantum processing unit. In the ideal case, that idle time is perfect, so it simply implements the identity operation, following which we, in an ideal case, would again just have the plus x state, again applied by a Hadamard, or acted on by 2 Hadamards, will be turned from plus x, as I'll let you see, back into the 0, 0 state. We will measure the expectation values, let's say in the z basis. So each of these will measure the z projections. And so we can compute 3 expectation values at the final stage here. And I'll bring myself over here to the left. We can compute the expectation value of zi, the expectation value of iz, and finally the expectation value of zz. And since in the ideal case, we're always in the ground state, you notice that the expectation value of zi is equal to plus 1. Again, recall that from the earlier slides, z acted on 0 is equal to +1 times 0. In other words, the 0 ket is an eigenstate of the z operator, and z acted on 1 is equal to -1 on 1. So it's also an eigenvector, but with an eigenvalue of -1. Again, we have +1, and in this case, if you want to more explicitly write it out, this would look like 0, 0 acted on by zz multiplied by 0, 0. Let's work this one out more explicitly. This is the same as 0 acted on by the first z here, and also acted on by this first ket here. Whereas the second ket and second operators here, we can move over to the right. And I know this may get a little tricky to follow all the signs, so why don't we use two different colors, in fact, to represent the two different qubits. Implicit in all of this are tensor products that we're not writing out, so maybe we'll just use this notation here to represent that the operators and states in black operate on and live in, respectively, the first Hilbert space, and the operators and kets in red operate and live in, respectively, in the second Hilbert space of the second qubit, equal to just +1 multiplied by +1, which in this case is equal to just 1. In other words, our three expectation values are all +1. A little bit boring, but it sets us up for a nice baseline for the ideal case. Let's look at what happens in the non-ideal case in that then. Suppose now, and this is actually not something to suppose, but you can even measure this, you find out that in most of the devices that you experiment with, there tends to be an interaction that's always on during any idle time, and during even any non-idle time, called the ZZ interaction. Suppose that during the idle time, the evolution is actually governed by a Hamiltonian, which I'll call, I'll denote by h hat, which is equal to 1/2 h bar omega zz. Whereas the first z acts on the first qubit, the second z acts on the second qubit. This is what we call the static ZZ error, and it's a coherent error because it's given by Hamiltonian. So what happens after a time t of having this idle time now subjected to this ZZ Hamiltonian? Let's look at the unitary that this Hamiltonian will generate. So I can write that as u hat of time t is equal to the exponential of -I h bar inverse times h hat times t, which is itself then equal to the exponential of -I omega t divided by 2 acted on by ZZ. You'll notice this looks a whole lot like our familiar rotation around the x-axis in the single qubit case, where we had Rx of an angle theta is equal to the exponential of -I theta over 2 acted on here by x hat. And in the single qubit case, we use the fact that x squared is equal to the identity in order to show that this equals cosine of theta over 2 times the identity minus I sine of theta over 2 times x. Well, we can play almost the exact same trick here, using, again, the idea that ZZ squared is going to equal the identity, because these operators act on different Hilbert spaces, so we can take the square on each independently, and the square of the z or the x or the y poly is always the identity, so this is I tensor I, which is just equal to the identity on the 2-qubit space. These are the identities on each qubit. This is the identity on the full 2-qubit space, which has dimension 4. So that's why, just for concreteness, I'm going to put a 4 here, but it's the identity on the total Hilbert space of the 2 qubits. In other words, from the point of view of the algebra, we have the exact same type of structure between this operator here on the right-hand side and this operator here on the left-hand side. Maybe we'll highlight this in pink to indicate that. And that's a powerful statement because it means that all the steps we did earlier essentially just follow the same, except now we're replacing x hat by z hat z, which is a multi-qubit operation as opposed to a single qubit operation, but nothing has effectively changed. So we can then use that to write that this must therefore equal cosine of omega t over 2 times the identity minus I sine of omega t divided by 2. And in this case, it won't be the bit flip operator, but it will be z hat z hat. So you've done your first really awesome multi-qubit unitary exponentiation here. And that gives us the Hamiltonian of, that gives us the total evolution after time t, which you notice looks just like a rotation, except in this case, the rotation is not around the single qubit axis x, it's a rotation around the multi-qubit axis zz. So I could, if you want, denote this by analogy with the single qubit case as a rotation around the zz axis of an angle theta that in this case is equal to omega t. So we'll see that coherent error in the single qubit case and in this multi-qubit case will act very much in the same way, where it has this similar quadratic buildup as well, because we saw that in the single qubit case. However, this time the rotation won't be as trivial in a sense, because this multi-qubit rotation will generate entanglement. And let's see that in the next step. The initial state that we start off with, we said was 0, 0. After the Hadamard's, this becomes the plus plus state. So far, we have the same evolution. However, now we have this rotation around the ZZ axis. So let's look at what that looks like. So now we'll have RZZ of, let's call it theta, acted on by the, by 2, rather, the plus plus state. Let's look at what that looks like. We'll notice that we can use our expression above. So we'll have cosine of theta over 2 times the identity times the plus plus state. So this will remain the plus plus state. So that's quite nice and simple. Then we'll have minus I sine theta over 2 times z acted on the plus state, tensor product with z acted on the plus state on the second qubit. So this is qubit 1, this is qubit 2. Let's see what z acted on the plus state looks like. So z acted on the plus state is equal to, and you can use this matrix notation if you'd like, it's equal to 1 minus 1, 0, 0. That's the Z matrix acted on the plus state, which is 1, 1 with 1 over the square root of 2 here for the normalization. And that's going to induce a phase. So rho A and rho A times column B, this will be 1 over the square root of 2 of 1 minus 1. If we come back up here and look at what the minus x state looks like, we'll see that it's exactly the same state. So essentially what the Z operator has done is to flip the plus x eigenstate into the minus x eigenstate. This is quite a nice and useful idea to keep in mind. Again, you can think of the Z operator as a rotation of pi angle pi around the z-axis in the Bloch sphere of a single qubit space. And so we always have this flipping from one side of the Bloch sphere over to the other side. Coming back and substituting this into the rotation above, we see that now our state here is going to equal a superposition between cosine of theta over 2 here, with an amplitude of cosine of theta over 2 between the plus plus x eigenstate minus I sine of theta times the opposite eigenstate of minus minus. This looks a lot like a Bell state, especially when cosine of theta over 2 and sine of theta over 2, you notice a little typo here, missing the 2, are equal in amplitude. In that sense, it's an entangled state. It can become a very, very entangled state. Now, there's one more step in our algorithm, which is that we apply the two Hadamard's again. So we apply the gate HH. Perhaps we should denote that here we're doing the HH, here we're doing the idle time. And thus, these Hadamard gates will, as you saw up here, they'll take plus x into 0, and they'll take minus x back into 1. And so we can write out the final step of this as cosine of theta over 2 0, 0 minus I sine of theta over 2 1, 1. And that will be the final state on which we now do our measurement. Let's compute the three expectation values again. The expectation value, and here we're going to change font size a little bit. We're going to compute the expectation value of zi. So let's go to, let's go to the expectation value calculation. So we'll do the expectation value of zi with that final state, the expectation value of iz in that final state, and the expectation value of zz in that final state. I'll leave this as a nice little test for you to try and challenge yourself. And simply tell us that we'll find the following three results. The expectation value of zz will be, zi, let's say, will be cosine of omega t. Of iz will also be cosine of omega t. And finally, of zz will just be unity. And this is again with respect to the final state that we found here. And look at the plots of these across, or rather, as a function of the delay time of the idle gate t here. We'll plot it in blue the expectation value of zi, in orange the expectation value of iz, both of which are essentially the same, and they are simply equal to cosine of omega t. It's clear here following. So both of these follow this cosine of omega t. Remember, omega here is our noise, it's the strength of our idle ZZ interaction. The ZZ value is actually perfect if you'd like, but we can use this to, again, see the exact same behavior as we saw earlier. These coherent oscillations, this coherent noise can really build up initially quadratically, and then it can take us all the way to the opposite side of our Hilbert space if it wants to, and can have a very strong effect on our algorithmic performance, since all of these are supposed to essentially remain at unity. So the error at a time here of 2 microseconds is quite large. We can repeat the exact same calculation as above for the difference between the ideal and the non-ideal expectation value here. And you see that the error is essentially So the difference between, let's say, the expectation value of Zi in the ideal case minus the expectation value of Zi in the noisy case is going to equal 1 minus cosine of omega t, which to lowest order is going to equal omega squared t squared over 2. And again, as in the previous case, we see that to lowest order, the way that the difference in the expectation value squares is quadratic with respect to the noise parameter omega. Which, if we just work out, is the expectation value of 1 over n times the sum on m sub n summed over all the shots, where n is the total number of shots. Let's be explicit about that. It's easy to calculate this because we can use the linearity of the expectation value. So you can take this at face, or let me just suppose we should do it like this, since each of these is a random variable. So excuse me, should be capital probably. But notice that each of these random variables of each shot, I've denoted them by m sub n, they're actually all the same. They're independent and identical. So we call that independently identically distributed, or IID. So really we could just use the letter m as a substitute for m sub n. So I'll just say that they are sampled from the same distribution. And I'll denote that here with this little curly congruence symbol. Then the expectation value, by the way, of a constant, a, times a random variable, whether it's x or m or something, where a is not a random variable, is just a times the expectation value of m. And the expectation value of a, let's say, m1 plus b m2 by linearity of the expectation value is just equal to the expectation value of m1 times a plus the expectation value of m2 times b. This is what we mean by the linearity of the expectation value. And using that in the sum, I can move the expectation value essentially all the way in through these constants and the sum itself. So this is just equal to 1 over n, the sum on n equals 1 to n, the expectation value of m sub n. But because all of these n shots are IID, we can just omit the subscript. And we can write this as 1 over n times n, since there are n terms in the sum, which again will more or less just cancel, times the expectation value of the measurement outcome m, which is indeed just equal to the expectation value of m. And that's precisely why the sample mean is defined in this way. And if we return up here north to our initial calculation, we'll notice that that's equal to this, which is equal in our case, as we've defined it, to p. So coming back down and substituting that, we'll see that this is equal to the expectation value, the quantum expectation value of the quantum operator m, which in our case we will just define as p. So maybe this is two results to keep in mind here. How the sample mean expectation value in the infinite case is equal to the quantum expectation value, which for a qubit is the following. This is very nice, but as we saw up here, we found that in one particular case, the sample mean was a third, and in the other case, it was a half. So that's not really telling us a whole lot then, in of itself, since we see that there are fluctuations around this mean. Of course, if we took the sample mean over all these possible realizations and took the average of that, we'll find out that we get this result. But for a single experiment where we take 3 samples, 3 shots, or n shots, we won't find that. So in fact, S can vary. And the question is, how much does it vary on average? And the way we can calculate that, in other words, what is the accuracy of our experiment? How accurately have we done our calculation? Is to ask what's the variance of this sample mean S, which is equal to the variance of 1 over n times the sum from n equals 1 to capital N of the nth random variable. This is a great exercise for you to try to work out manually from the definition above. If you want to be quick and short about it, we can use a few identities, which I challenge you to prove for yourself, just following the definition of what we mean by the variance. But essentially, the variance of a constant times a random variable is equal to the constant squared times the variance of the random variable itself. And the variance itself is a random variable. Sorry, the variance of the sum of 2 random variables, like this. Let's say that it's a constant times x plus b times y, and y is a random variable, is equal to a squared times the variance of x plus b squared times the variance of y, plus, in general, a term that speaks to the correlation of the 2 variables, or the covariance of x and y. Now, this term will be 0 for all of our cases because we won't be looking at correlated measurement outcomes. They're independent and identically distributed, so we don't really care what the correlation is. But just for explicit, just to be explicit here, we can write this out in the following way. But again, in our case, this term is going to be 0. So using this notation, we can say that the covariance, by the way, of mn and mn prime is equal to 0 for n not equal to n prime. And so this will then equal just 1 over n squared. Remember that the variance is a quadratic quantity, so we will have this. We can pull out the sum here as well. So we'll have the sum from n equals 1 to n, the variance of m sub n. The variance of m sub m is just equal to the variance of m, just one of the outcomes, which we calculated above. And if we come back to our result above here, we'll notice that it's p times 1 minus p. So let's substitute this all in, taking into account that because of the sum we have n of these terms. So we find that the variance is p times 1 minus p, where p is the probability to be in the excited state, or the 1 state, divided by n. In other words, and perhaps maybe it's worthwhile to also write this in the more general sense, that this is just the variance of n divided by n. So in fact, what you can do from this curve right away is figure out how to measure this matrix. And this is going to be pretty easy. So one thing you could then do is to say that the way to reconstruct the readout A matrix is to prepare the 0 state, which would be preparing this state, and then measuring our, maybe we should put it like this. It's probably a little bit easier to read this. So suppose that we now prepare the ground state 0. We perform our measurement, which gives us the ideal value m is equal to 0. Now that value of m equals to 0 is processed by the A matrix, which here I'll just schematically write like this, to give us a new value for m tilde. In One way we could write it as here's the probability which is associated with P is just equal to 0, meaning we're in the ground state, it should be 0. If we now look at what P tilde is equal to, and coming back up here to the expression, plugging in 0, we'll see that that's just equal to epsilon. And so, in fact, the location of the lowest point here is exactly epsilon. So this is how we can already find what epsilon is. If we know epsilon, we've now learned the entire first column, of the A matrix. So we've just learned this column of the A matrix by doing one experiment. Of course, because of projection and shot noise, you'd have to do this with high accuracy with some error. So you'd want to do this many, many times over and over and over again to have a high estimate or high fidelity estimate. Now suppose that we instead prepare the one state, which we could do in the following way. So we start with, say, 0. We apply an ideal X gate, which is then followed by our ideal measurement, which gives us the variable m. Now with probability p equals 1, since over here at this state we would have the state 1, this stage we would have the state 1, that variable m is then in our model processed by the readout A matrix, which is a classical thing. And the readout A matrix now will give us the variable m tilde. This is what, unfortunately, we only have access to. We don't have access to m. And p tilde is then equal to, as you can go back up to the expression here, this term will now be 0 and will instead see only the 1 minus nu term. So this is going to equal 1 minus nu. And so that will be this term here. So instead of epsilon, we'll now have 1 minus nu on this side up here. This is at level 1 minus nu. This is at level epsilon. And so the distance between these two is, of course, 1 minus nu minus epsilon. This is going to be your contrast of the measurement. So this is how we've now reconstructed the second column of the A matrix. So this is how we can learn with some accuracy the total A matrix. If we know the A matrix, and because you can see from this, this is an invertible result. Suppose that we observe the value, let's say 0.9 approximately. Suppose that I measure 0.9 as what my m bar value. I can then look at this curve, go back, oops, excuse me. With this curve, you'll never measure 0.9. Let's pick something else. Let's say you measure the value 0.51 or so, roughly. Some value that's over here on the y-axis. We can go back to the noisy red curve and use that to figure out that actually what we should have measured is maybe 0.65, roughly, right? We can undo the effect of this noise. Now, mathematically, how can we do that? Well, we can do that in the following way. So we'll call this our first type of noise mitigation. Using the inverse A matrix. This is something that's built into Qiskit and you can use. So once we have learned what the A matrix is, we'll say that it's a known. We know what the A matrix is. We now observe or measure a probability vector for m tilde, from which we can basically find p tilde. So we know basically the probability vector p sub m tilde, and we'd like to find the ideal vector p sub m, as well as the ideal noise-free expectation value p. And you can do this very easily, since from above, if you recall, we know that Pm tilde is equal to A times Pm. If A is invertible, then we have Pm is equal to A inverse Pm tilde, from which you can then calculate
what your P M is, what your ideal P is as a function of your noisy P. And that just amounts to using this curve to undo the effect of noise up here at this level. In general, I'll just note that that's not necessarily an easy task to do in general, because our noisy and ideal vectors and A matrix scale exponentially. We'll note that the dimension of the A matrix is 2 to the n times 2 to the n, where n is the number of qubits. So for a modest number of qubits, even this can become quite expensive, and they're much more clever works. I can recommend you to see some of them. This is work ongoing. But you can also use random gates to mitigate some of this in a recent paper that we put out with some colleagues of mine. That aside, one other really important feature in this is the visibility, or essentially the fidelity, because you notice that A can become non-invertible essentially when the red line becomes flat. Then you can't have this one, then you lose this one-to-one mapping. And so we will also define, as you'll see sometimes written in the reports of different quantum devices, this as 2 times the fidelity of this particular measurement. This is called the assignment fidelity. It tells you what your contrast is. Clearly, if nu and epsilon become 0.5, the line is flat, this fidelity f will become 0. And a little bit more formally here, we can write out that the fidelity, the assignment fidelity, is defined in the following way. It's defined as f0 is equal to 1 minus 1/2 the conditional probability of measuring m tilde is equal to 1, condition on m being 0, plus is basically the average of the two errors, plus the probability of measuring m tilde is equal to 0, given that m is equal to 1. Which is in general written as 1 over d, the dimension of the Hilbert space, which in our case is 2 to the power of n if you'd like, but let's just leave it as d since that's a bit more generic, times the trace of the A matrix, which is just equal to 1 minus 1/2 mu plus nu, basically the sum of the two errors. And we can define that d is equal to 2 to the n, where n is again the number of qubits. One other very illustrative way to think about this and to understand what happens as a function of the error here is to look at the entropy of this classical channel. Think about the Shannon entropy in particular. So let's take a quick look at that. So what is entropy? Entropy is a key concept in measurement theory and information theory, and in particular in quantum information theory. Entropy measures how much uncertainty there is, but in a different way from standard deviation or variance. One way to understand entropy is to think of the entropy of M, the measurement here, as a measure of the amount of uncertainty about M before we learn its value. In other words, if we already know what M would be, such as we know the state, we know that there's no error and the state is 0, then M would have 0 entropy. We don't need to measure it if it's a deterministic quantity, but if it's a random quantity, then there's a question of how random it is. If it's mostly zeros, then it has very little entropy. But if most of the time it will be 1, then it also has very little entropy. The entropy doesn't care about the labels. But if we have total randomness, such as a probability of 0.5 to measure M, then we'll have maximum amount of entropy.
Now, entropy has a number of very interesting features. We won't get into that, but the Shannon entropy of M, in other words, can also quantify how much information we also gain on average when we learn the value of measurement. And this is all measured in units of bits. So just to remind ourselves here, let's take the entropy of the variable M, here denoted by this H. This can also be understood as a function H of the probability distribution. We'll call that as P sub M. And this is equal to, for the noiseless case, minus the sum on M, the probability of measuring M, times the log in base 2, the probability of M. This is because we'll use bits to measure the amount of entropy, so that's why we have log 2. And so this is equal to the negative of 1 minus P log in base 2 of 1 minus P times log in base 2 of the probability P. This particular function is also known as binary entropy and comes up many times and is well known in quantum measurement information theory. Let's look at a visual representation about this. You can derive the one as a little exercise in the case of the noisy version of this. But really at this point we are only more interested in the qualitative behavior of this. So for the two examples that we looked at above, suppose that we have in red the noisy version with these noise parameters of 8% and 20% error, and in gray we have the ideal version of the entropy measured in bits. We'll notice that the entropy is maximal in the ideal case exactly when we have a maximally random coin toss or bit at a value of P of 0.5, and we have exactly 1 bit of entropy, 1 bit of uncertainty. On the opposite end, we have exactly 1 unit of information in units of bits if we have the deterministic state 0 or 1 and no noise. But if we have noise, M in itself no longer can fully reveal that, so we no longer gain 1 unit of information in that case, or we no longer have that full information since we also have to take into account what the noise will do. And you'll see that even for this modest amount of noise, the entropy becomes quite high quite quickly, and we never find ourselves lower than about 0.4 bits of noise. Our entropy never goes to 0. We always have at least 0.4 bits of noise for whatever input state we put in. And we'll see that the maximum entropy is a little bit shifted from the 0.5 to a slightly different state. But essentially, overall, there's just more entropy. And the amount of excess classical entropy, not entropy due to the quantum indeterminism. So perhaps one way to write it is that the gray curve tells us about the quantum entropy, and here the red shaded area is, in this case, the excess classical entropy. When you take this to a larger system, essentially the same results generalize. And we have the exact same idea also with the A matrix. Suppose we now have several qubits, let's say n qubits. Then we know that the dimension of the A matrix for all the possible measurement outcomes is 2 to the n times 2 to the n for all the possible inputs and all the possible outputs. Now our measurement inputs and noisy measurement outputs can in general be sequences. So let's just say that we have 2 qubits, just to illustrate the point. There are 4 possible measurement results, 0, 0, 0, 1, 1, 0, and 1, 1. And similarly for M0 here, we have 0, 0, 0, 1, 1, 0, and 1, 1. And now we have the noise-free cases, or the ideal arrows, but as you notice, there are potentially many more paths of noise that could occur. And so the A matrix becomes quite potentially difficult to calculate and keep track of. So you have to be a little bit more clever in the way you construct it and think about it. The complementary noise to measurement noise is that of state preparation. And one way to think about state preparation errors, or state prep, is to say that instead of starting with the ideal state that you would have expected, which is the ground state 0, we sometimes, with some probability, start with the state P. So instead of executing the circuit at the top with probability, let's say P, we execute the circuit at the bottom. And in this sense, we have a mixed state to begin with, and we'll see what I mean by that in just a second. But of each instance, you could almost think of as a single ideal trajectory with a pure wave function where we've simply started with two different states. The challenge here, of course, is that this is simply uncontrollable. We don't know which of these two circuits we're going to execute, and at the end, we'll get a measurement outcome, we'll call it M, that comes either from this circuit or from this circuit with some probability 1 minus P and some probability P. And the measurement outcome we'll report is M. But clearly in these two cases, M will be very different. Here I'll denote the outcome of the first circuit as, let's say, M sub 0, and this one as M sub 1. We'll note that in the case that we suppose that U is equal to the identity, basically nothing happens, let's just make it as simple as possible, then M sub 0 is equal to 0, M sub 1 is always equal to 1. In other words, the probability of M here is really equal to 0, and the probability for M here is equal to 1. And so our final M that we do measure is essentially going to be equal to the following. It's going to be either 0 or 1 with some probability, and the probability is going to be given by, in this case, let's change the color so as to indicate that this is for our example. We'll make that gray. This is with probability 1 minus P, and this is with probability P. Excellent. So this is maybe the most simple example of state preparation, but how do we describe the evolution and the dynamics and the statistics of our final observable and our state as we go through this over time? Notice, by the way, that one way you could also think of this is simply that you had a random bit flip gate here to go from 0 with some probability. You apply the X gate in order to get to 1. That probability is P, and you would have the same outcome. But this is maybe more of a side comment, so we don't need to get into that right now. Now, in quantum mechanics, the way we can describe the unitary evolution as well as the evolution that's due to each of these two different possibilities is by using the idea of the density matrix, or the density operator, which is defined in the following way. So at time 0, we'll look at our initial state. We'll say that the operator, the density operator rho, is equal to the projector onto the ground state. This is one of the initial possible states, 0, 0, plus the projector on the other possible state, the 1, 1 state, but each weighed down by their respective probabilities of occurring. So this looks, if you think about it, a lot like the observables we saw earlier, but is a bit different because here really we're thinking of these as states. In fact, this corresponds to the pure state 0, and this will correspond to the pure state 1. But now we've mixed the two states and made a incoherent, partially incoherent random combination of the two. And we'll see that the dynamics of all the rest of the physics just follows all the same. Essentially, we've said that the density matrix that we start with, the initial state, is equal to the probability of no error times the no error state, or the ideal state. So I'll just call that rho ideal. I'm just rewriting the same expression, plus the probability of an error times rho in the case of an error, where, of course, rho in the case of an error is this, the probability of an error is p, the ideal state is the following, and the no error state is the following. The dynamics of the system evolves in more or less the usual way, where a unitary now is applied on each of these operations. So if we now want the state rho at the final moment, let's call it rho sub f for final, think about how we would normally evolve our states. We would apply a unitary u on psi, which would give us the final state psi. Notice that if we, of course, complex conjugate each of these, then we would have the fact that psi final is just equal to psi applied by u dagger from the right. And so we can see that the final state in each case is simply going to be ideally equal to the probability of no error times the ideal density matrix in its final state plus the probability of an error times the density matrix in the final state of the no error case. We can write each of these out up here explicitly to show what those are, keeping the same construction. So this is going to be equal to 1 minus p times psi final condition on having started in 0. Again, psi final condition on starting in 0 plus the probability of an error times psi final conditioned on the fact that we started in the 1 plus psi final condition on the fact that we started in 0. We can calculate each of those independently, but again, seeing as they're both evolved under the same exact unitary always, we can take that unitary and replace it. So this will be u 0, 0, u dagger plus p acted on by u 1, 1, u dagger. Seeing as how we have u's on each side, we can factor out the u's. So we have u 1 minus p 0, 0 plus p times 1, 1 u dagger, which is indeed just equal to u rho u dagger, where rho is our initial state defined up here. So this is the general evolution of a density matrix under a unitary, is to say that rho under some unitary u is equal to u acted on rho times u dagger acted from the right. And we'll see that essentially you can think of this in the sense of a trajectory, that the unitary, that you can think of this entire composition as simply having a pure quantum trajectory of a pure quantum state starting in the 0 state acted by a unitary that gives us the final state condition that we started on the 1, on the 0 state. And similarly, you start in the 1 state, pure state, apply unitary in the pure state. You find the final state here is psi final at time condition on starting in the 1 state. And the way you combine these is, again, as shown and defined down here as well. And so this is how we can combine this kind of indeterminate mixed dynamics, indeterminate in the sense that we are not having all the information about the evolution of the quantum state, because if we did, the evolution would be purely deterministic and well-known and pure. Here, the evolution is still deterministic, but we have to average all the different trajectories together. If you think of each of these states as a block vector, we're now adding together several block vectors that are all pointing in potentially different directions. and we're weighing them by the probability of having that evolution. And so that will, on average, shrink our block vector down. And let's see what that looks like. So suppose that we're a little bit maybe even more explicit about this in terms of Pauli operators. You notice that we can now write down the 0, 0 state as 1, 0, 0, 0. And of course, we can write down the 1, 1 state as 0, 0, 0, 1. So if we combine both of them in matrix notation, the initial density state will be 1 minus p, 0, 0, p. These are written in the logical basis, like this. In terms of Paulis, it's also useful to note that in terms of the Pauli matrices that we've introduced earlier, this is simply the identity plus 1 minus 2p times z Pauli operator. The expectation value of, say, the x operator, the x Pauli, is equal to the trace of x row. Similarly, the expectation value of y is equal to the trace of y row. And the expectation value of z is equal to the trace of 0. Each of these in turn will give us a value. Now, for this particular state, we're going to find out that the x value is 0, the y value is 0, and then the z value is 1 minus 2p. How did I know that? Well, that's because in the first two lectures, you must have seen that the Paulis are orthonormal in the following sense. The trace of Pauli 1 times Pauli 2, say p alpha, p beta, is equal to delta alpha beta times the identity for alpha beta in x, y, and z. So basically, the x, y, z Paulis will give us, oh, excuse me, and there's a 2 here. The XYZ Paulis will give us 0 as an when they're traced out. This is an inner product in this operator space. The inner product between two Paulis is 0 unless it's the Pauli with itself, unless they're the same Pauli, in which case you will find out that we have just 2. There's no I there. Excuse me. This is a number. It's a scalar number. There's no operator to describe. These expectation values of x, y, and z then give us the length of the block vector as well as what the block vector is. So if we now have to depict it on a picture of the block sphere, where the value of p equals 0.2, so we have about 20% chance to randomly be in the 1 state. This is an incoherent probability to be in the 1 state, very different from the coherent probability. That's why you see that the block vector isn't simply rotated, but it's actually shrunk in length, because essentially this is equal to the sum of a block vector that's unit length pointing up and one that's unit length pointing down. So let's say 1 and 1, and these two are summed, but the first one has a probability of 1 minus, times 1 minus p, where p is 0.2, plus this, but times p, which is 0.2. So summing those two, essentially you end up with this vector, which has the location in the block sphere of 0, 0, and 1 minus 2p. Or if for our p of 0.2, this is about length of 0.6. And so no longer is the block vector on the unit sphere, it's now shrunk. This is an indication of the state being mixed and impure. One way to quantify how mixed or how incoherent or impure the state is to look at the trace of the density matrix squared, which is called the purity, which is just equal to the block x vector x squared plus y squared plus z squared. This is the length of the block vector squared, if you want, which is, in our case, just equal to 0 squared plus 0 squared plus 1 minus 2p squared, which will give us the purity. And you notice that for this particular p, this function will take the following form, where we have the probability going from 0 to 1 and 0.5 being in the middle. When the purity is 1, we have a pure state. There's no mixture. There's only two possible cases when this will happen, and those are the extreme points of P. So when the probability is exactly 0 or 1, meaning that we deterministically prepare the 0, 0 state, and here we deterministically prepare the 1, 1 state, we have a purity of unity. Otherwise, we always have a purity of less than 1 with a minimum of 0. This is the trace of rho squared. And the worst case is when we have a 50% chance to be 0 or 1. In fact, the length of the block vector and the purity both go to 0. Let's now scale to larger systems and see what that looks like. Suppose that we have this n-qubit system that starts in this mixed state. Each qubit has the probability p of being in the excited state, and we have this product state. So writing this out, what you'll find is that the initial density matrix going into this algorithm here, assuming we have this probability, is equal to, again, 1 minus p 0, 0 plus p times 1, 1. The whole thing raised to the power of n per qubit, which we can expand, and it's a bit tricky to fill in all the terms, but let's just do the simplest one, which is the probability of the all zero state. So the state that has 0, 0, 0, 0, all zeros for all n qubits. This term can only be obtained from the binomial above by only one combination, and that's if we get a 0, 0 term from every single of the n terms. So that's 1 minus p to the power of n, since each of these terms here will bring exactly 1 minus p. And we have n of those multiplying together. Then there's a number of more terms, such as the 0, 1, 0, 0, dot, 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 and so on. But we don't need to write those out explicitly, because usually what we're interested in something like this is actually to find out what is the probability of finding the initial state, rho 0 here, in the O0, or what's the probability to measure the O0 state. So perhaps we can write that in our more usual notation to say that m equals the string 0, 0, 0, 0, 0, etc., where we have n of these zeros. Well, in the case that there's no noise, we certainly know that we should be in the ground state when p is 0. So clearly the probability of this is unity. So if p is equal to 0, which is the ideal case, then we just have 1. However, if p is finite, otherwise we'll have 1 minus p to the power of n, which in the limit of small error, or small p, is approximately equal to 1 minus n times p plus order p squared. This is for p is greater than 0. So we see that we have, for small error and small number of qubits, a linear increase in the infidelity of measuring the all zero state. Similarly, for the expectation value of different observables, such as the poly z observable on the kth qubit, which here I'll just quickly denote by z sub k, meaning that we have I, where this is at site k, I, bit string, so and so on for the n qubits, is therefore just equal to 1 minus 2p. And this is the same as for the single qubit case. There's only one way to extract from the sum up here above this term. However, if we look at the probability of the highest order bit string, not a single poly z, but something like z, so on, the all z bit string, we'll instead find something that's a lot more tricky and heavy. This is equal to just z to the power of n inside the trace with rho. To understand what this product looks like, it's easiest perhaps if we rewrite rho 0 in terms of a product of polys, which we can write like this for each qubit k from 1 to n. We have a tensor product of the individual density matrices, which I can write as the identity on the kth qubit plus 1 minus 2p times the z operator acted on the kth qubit, which, if we expand, is going to give us 1 over 2 to the n I plus some coefficient times z, tensor I plus the same coefficient times z, tensor the same thing over and over again, or in terms of a sum here will equal 1 over 2 to the n 1 minus 2p to the power of n z tensor n plus ... all the possible combinations of the binomial here. And we'll notice again that the only way here to get the all z term is to, from each of these terms, pick out the z. So that's why the coefficient here is 1 minus 2p to the power of n. Therefore, the expectation value of our term up above here is this coefficient, and so it's 1 minus 2p to the power of n. You notice that that decays exponentially faster and scales the number of qubits here compared to the single qubit case. And that's because essentially the probability to have an error is really high now because there's so many ways that that could happen. Qubit 1 could have an error, qubit 2 could have an error, qubit 3 could have an error, qubits 1 and 2 could both have an error, and so on. And the way to have no errors, the probability to have no error is 1 minus 2p to the power of n, which decays exponentially fast. You could also look at the purity, and you see that because it's a product state, the trace of rho squared is just equal to product of from k1 to n of the trace of each of the individual density matrices for the kth qubit. So you can multiply that out, and I leave that as an exercise for you. Instead, I think I'd rather just plot here the result of that purity, which looks like this. Maybe let's just work this out. This is the purity of the kth. Well, actually, if we come back here, we have the expression for the purity. It was 1 minus 2p squared. So then this will become 1 minus 2p to the power of 2n. So that's the rate at which our impurity decreases as a function of n and p, the number of qubits, and the probability per qubit of being in the excited state in an incoherent way. So for 1%, 2%, and 5% probability for n number of qubits on the x-axis, you'll see that when we have even just 1% error, but we have 50 qubits, we're already starting with an initial state that has a purity of almost 40%. So keeping in mind state preparation with large number of qubits as the main source of error and infidelity is really important, because your infidelity starts out very, very high here.